So today we are going to finish multiple sequence alignment methods, and I'm going to quickly go over the midterm exam topics that you're responsible in the midterm that we're going to have on Monday morning. Um, if you're having difficulties of starting the exam at 9:40 because of this COVID thing that everybody needs to be, only we are allowed to go outside at 10, between 10 and 4, and if you plan to be somewhere after 10, we may actually start the exam not exactly at 9:40, a little bit later than that, maybe at 10, but there may be some schedule clashes with people having classes after the regular class hours, so that may cause problems. So, but if you really have a big problem of being not able to start the midterm at 9:40 on Monday morning, please let me know by sending me an email. All right, so the midterm exam is going to be an auto class. The exam, you're going to see the exam at the top of the auto class course page, and you will be able to attempt it starting at 9:40 on Monday. And I will be checking my emails regularly. So if you have any questions about any parts of the exam, if you have difficulties in certain parts, technical difficulties or anything, please send me an email, and I will try to get back to you as soon as possible within a couple of minutes. I will be checking my emails regularly. Okay, so do you have any questions before we start? All right, let's then continue with the multiple sequence alignment methods, and let's finish these today. So we have seen the greedy two alignment algorithms up to now, actually multiple sequence alignment algorithms. The first one is this greedy approach where we align the most similar sequences at every step. We find among the k sequences, we perform k-choose-2 alignments where, this case, k decreases at every iteration by 1. But in this was the greedy method that is described on the slides. So this greedy approach, we were choosing the most similar pair, a single pair at every iteration, align them and combine them to a single profile. Then this profile becomes part of the sequences. The two sequences themselves, they're deleted. They are now combined together as a single entity, and we continue doing this until only one sequence left. This is similar to clustering methods. We are going to see when we talk about microarray techniques. This is what is called agglomerative clustering. Let me write in the chat box. Maybe I may have misspelled it, but it's something like this. It's a difficult term, which means that combining, like cumulatively, by starting at individual instances, at each step you group a pair of instances into a cluster, and then hierarchically you continue this process until you get a single cluster. We are going to talk about these when we talk about microarray expression analysis, we are going to see. But this is basically the same idea, combining a pair of sequences at every step. In the following step, again, we decide among these k-1 sequences, we decide which two are the most similar. So this new sequence is aligned to the rest of we don't spend k-squared time this, and we don't need to do that because the new one, the sequences other than the new one are already aligned pairwise with each other in the previous step, so we don't need to do the alignment again. We only align the new profile against the remaining one to see what the score of it is against the others, and again choose the most similar pair from here. It may be this one and this one, this time the most similar, and they don't look like similar, or maybe I chose a wrong example. They're all the most dissimilar one. If there's another thing with TATs and AAs here, okay, TAA, for example, T. So the next most similar pair of sequences may be something else other than the one that was chosen in the previous iteration. And this continues all the way to the end. We have also seen the star alignment method, in which we find the first a single sequence which we choose as the center of our star, and we use the alignment of other sequences to that as a reference. We use only those alignments to build the final multiple sequence alignment. So the first step is we calculate k-square different pairwise alignments given k sequences to align, and we choose one sequence which maximizes the total sum of pairs score among all the other sequences. That if there are ties, in any case, when we have these greedy algorithms, when there are ties, which means that if two sequences obtain the same top score, we usually break the ties randomly. Okay, so in case something like that happens in the exam, if there are ties, for example, you can just arbitrarily choose any one of them as your maximum result. As the next step to proceed. So this one, in this example, S2 is deemed most similar to the remaining. But we have solved this example, if you remember last time, we have solved this example by using a scoring scheme where match was like -3, mismatch minus, or 4, -3, and -1. It was something like that, I guess. But here, the score is not given to us. You're just given in this. If you try to study this slide, you'll have some questions. Why is S2 chosen as the center? This is not specified in this slide, okay? Probably, and the pairwise alignments S2 to the other ones, they are given. The slide only just says that S2 is chosen as the maximum best scoring sequence, maybe with some mismatch scoring gap penalty. S2 may indeed be the most similar to the remaining to the other sequences, and these show the alignment of S2 to the others. All we do is we start with one of those alignments and the new alignment. So here S2 is MKE, so MKE aligned with MPE, we start with that one with no gap. Okay, then when we add MSKE, alignment of S3 to S2, when you put the MKE, MSKE alignment, this alignment here, MSKE is put like this, and there's a gap here. When this gap is introduced here, if there was no gap in the previous case, it's introduced in all the other sequences. So the previous alignment, MPE aligned to MKE, is still the same alignment. Again, by the way, let me increase my mouse pointer size quickly. So this is the same. Okay, so this alignment, these two gaps that are here, if it was pairwise alignment, we wouldn't have these two gaps in an alignment column. So it's actually what you see here in the first two rows is exactly this alignment here. So this was star alignment that we have seen, and it may have certain problems that we talked about. If there is no single center sequence that is just similar to everybody, all the other sequences. What if there are two groups or subfamilies within the groups? As we have seen in the Bali benchmark last time, there are some challenging cases, for example, where there are subfamilies within the set of sequences that we try to align. So this may also be possible. In that case, star alignment is not going to perform in its best. It may produce some errors. And we also did the running time analysis of star alignment. The first step of finding the center takes dominating time complexity. The remaining steps are actually combining the pairwise alignments into a single alignment is the easiest step. Now we come to cluster W, or cluster omega. So this W, I think in the original case, this is clustered weighted. So W stands for weighted, and it was the English letter W. So it's not cluster omega. But if you make it a Greek letter, then it becomes cluster omega. I think, yeah, the initial version was cluster W. There is an improved version these days that you can use named cluster omega. It's one of the most popular multiple alignment tools, along with TCOFFEE and Muscle. It's a three-step process. I'm not going to go into the details. The idea is the same. It's a progressive alignment. It merges multiple pairwise sequence alignments are combined together as a profile. Uh, and for example, if I remember correctly, in cluster omega, for example, those profiles were represented by using profile hidden Markov models. So how that profile is represented is something that you can decide on. All these different parts of the alignment algorithms, they're heuristics that they provide at the end approximate results. So in the first step, it constructs pairwise alignments. So the first step is the same as the star alignment. We pairwise align all sequences that are given to us. So we perform in OK square n square time, where n is the average length of these sequences. We conduct pairwise alignments. These pairwise alignments gives these alignment scores can be then put together in a pairwise similarity matrix. For example, if I have k sequences, I can write here S1, S2, S3, S4, all the way to Sk. Again, here S1, S2, S3, all the way to Sk. Maybe we are not aligning the same sequence against itself, so we can have all zeros here on the main diagonal. So this is a square matrix, as you can see. It's a k by k, or let me write it in matrix form. It's a k by k matrix. The main diagonal may be all zeros, indicating the distance to all of each sequence to itself is 0. So 2 points. First, the sequence alignment score. If they are given to us as similarity score, we may have, instead of having 0 here, we may have large numbers, or we may completely ignore this diagonal. So the thing that I'm trying to say is a cell here indicates some relationship of two sequences Si and Sj. Okay, whether this is similarity score or whether it's distance, like the edit distance or Levenstein distance or Hamming distance. Since it's an alignment, usually it's going to be some format of edit distance. But whether this is distance or similarity is actually not so important, because similarities can be converted to distances and vice versa. But what this matrix is really important. We are going to be using such a matrix to build the phylogenetic tree, or a hierarchical clustering of these sequences. Okay, so this is what we are going to do is use these matrix, and in cluster W, they use the neighbor joining method to build a tree. So this is what we are going to see after the midterm. We are going to start this new problem. It's a very nice computational problem, and actually I have in the first week's lecture where I gave a sample lecture, I talked about one of these algorithms which uses the additive distance matrix. So the problem is, given these similarity scores, can we have a binary tree that shows hierarchically the relationships between these sequences, and we'll have these sequences at leaf nodes and the edges of these trees. This tree is going to have some weights, and the path distance between two sequences here, we will try to make it equal to the distances that are given to us. If this is a distance matrix that is given to us, we will try to make the distances equal to each other. So this is what the cluster W does in its second step. It uses the neighbor joining method, which we are going to see, to build a tree. This tree is something like this. Let me show you. So this is a guide tree. What does this tell us? It tells us that V1 and V3 are the most similar sequences to each other. You first align them together, then the resulting profile should be then aligned to V4, then the resulting profile should then align BV2. So this is what what I just said is written in terms of alignments. Okay, so this guide tree this is not like a balanced guide tree. It's like every time we are adding a new sequence, but there may be trees in which, for example, look at this one. This tree shows that align S1 and S3 first, and align S2, then align S2 and S4, or you can do these in parallel if you write your multiple sequence alignment algorithm in a multi-threaded manner. Alignment of S1 and S3 and S2 and S4, these two things, step 1 and step 2, they do not depend themselves in terms of order. They can be ordered in any way, so they can actually be run concurrently. Okay, but after we get the alignment, the alignment in these two things, these intermediate nodes, then they're aligned to each other by using neighbor joining, by again pairwise alignment. So neighbor joining gives us this tree. Given this similarity or distance matrix, by using neighbor joining, we get this tree, and then the tree tells us how to combine those alignments. So it's as you can see, it is the same idea of greedy. I mean, it's progressively builds the alignment, but the star alignment, the restriction is that we have our tree, our phylogenetic tree looks something like this. I mean, we always have one sequence at the center, and we use the alignment of that, and then alignment of that to the other. So it's basically maybe considered a tree that is like this. Okay, so if this is one of the center sequence here, if this is your S1, you first add on S1 to S2, but the profile isn't aligned. In star alignment, we don't use profile alignments. The different thing in star alignment is that we always use the pairwise alignment to S1, so S1 and S2 pairwise alignment, then we add to that S1 and S3 pairwise alignment. So profile alignment is not used in star alignment. But the idea, as I said, is not so difficult in cluster W. The only different thing is that it allows for subfamilies to be considered. If we have subfamilies of sequences in our multiple sequence alignment, the neighbor joining guide tree is going to reflect that. We are going to first align those families, subfamilies of sequences among each other, and then combine them together in the next step, which will basically lead us to make less errors, because we're going to be aligning most similar sequences first. So let's see whether there's anything I miss here. And then, yeah, this progressive alignment is guided by the tree. The sequences are put together in profiles by using the branching order in the guide tree. So there's the similarity matrix can be anything. So doesn't cluster, I don't know what cluster W uses for computing the similarity between these sequences, but it could be percent identity, it could be the Blossom 62, it could be the total alignment score between those two sequences. It may be the distance, edit distance. So yeah, a question? Oh, no, okay. So yeah, the matrix here, the similarity matrix or distance matrix, could be using any similarity or distance measure between these two sequences. Then, by using this matrix, we build the guide tree, and cluster W uses neighbor joining method, which we are going to see after the midterm. And by using that guide tree, we progressively build the alignment. So that's all you need to know about cluster W in this course. Sometimes the results shows us which parts are more conserved. So the dots and columns and these stars, they show how conserved the column is. So it gives you an idea about how good the alignment is. Here's another example of cluster W, 4 sequences. We first get the pairwise alignments. This time we get the distance matrix. As I said, whether it's similarity or distance is not that important. One can be converted to the other. And after the distance matrix, we use neighbor joining to find this tree. This tree tells us the order to combine these alignments. And after that, we get ourselves the multiple alignment. So we first align S1 with S3, we get this. Align S2 with S4, we get this one. And we align these two profiles with each other to get our multiple alignment. There are other progressive approaches. So I didn't mention this other tool, pileup. Pileup is another method which uses again a guide tree, but this time the guide tree is built using another technique, UPGMA, which is another phylogenetic tree building method to build the guide tree. We are going to see UPGMA also. The progressive alignments usually they also depend on pairwise alignments, as we did in star alignment or greedy alignment. If the sequences do not share even at the leaf level, two sequences that are put together in the leaf level in your phylogenetic tree, if you have something like that, there is more likelihood of errors. You cannot avoid that. And how you compute those similarities, distances is really important. So you have to be very careful in choosing your scoring matrices, penalties. Here's a figure from which we discussed this earlier. It shows the limits of the progressive strategy, meaning that we start with pairwise alignments, we build alignments along the way. The thing about progressive alignment is that when we use an alignment, we don't go back and make changes in the final alignment. So there are improvements to this, to progressive. There are hybrid methods which use also progressive, and then after we get the final alignment, iteratively we can try to figure out whether we can get this alignment better or not by making small changes on it. So this is like we first do like a hill climbing, and then we try to look at the neighboring hills, whether there's a better score there or not. For example, if this cat you see is moved 3 to the right, it will have a perfect match with the other 3 sequences. So there are iterative methods, or these methods which randomly make certain changes and searches and see whether the alignment gets better or not. So this is called iterative refinement. So that's the progressive strategy. When we make changes, when they are fixed, frozen, we will not be able to change that later. But iterative refinement, the idea of iterative refinement is to make these small changes to make the alignment better. And yeah, these are some. We actually went over the different benchmarks. The Bali-based benchmark, we have seen how different sequences there are, and they are constructed manually by using structural similarities, as structure is more conserved than sequence. And it's been more than 20 years that Bali-based benchmark was first introduced. And the quality usually, when you're comparing several algorithms using this benchmark, you see how these algorithms capture the conserved blocks in Bali-base. There's another submark benchmark. Let's see whether it still exists or not. Submark benchmark, MSA. Oh, the first thing that comes is our class webpage. So, wow, this is let's see, a benchmark for sequence alignments that covers the entire known full space. So it was a 2005 paper. This benchmark was first introduced in 2005, and it uses the structural families, the scope database to perform this, just like similar to the superfamily database, which was also using the domain definitions from the scope database. So these structural databases that show relationships of protein structures with each other, they are used a lot, as you can see in different places. So how do we score multiple alignments? When we have a multiple alignment, how do we score that? I mentioned a number of scoring mechanisms like the sum of pairs score. Since a multiple sequence alignment induces pairwise alignments, we can compute the pairwise alignment score of each of these pairwise alignments and sum them up. That may be our multiple sequence alignment score. So that's called the sum of pairs score, which is also very popular. There is entropy-based scoring, compute the entropy of each column of the multiple sequence alignment, and then again add them up to compute the overall entropy. And these measures usually assume the independence of the columns as we did in pairwise sequence alignment. So other multiple alignment scoring mechanism, for example, the total number of matches, multiple longest common subsequence score. So the entropy score and sum of pairs score, I described those. And this is the end of my slides. So this concludes multiple sequence alignment. And I'm going to now go over the material. Let me go to the schedule website. And I will be happy to answer any questions if you have any. Okay, but yeah, this one concludes our multiple sequence alignment, discussion on multiple sequence alignment. No, actually Clustal Omega or Clustal O, Clustal W, there are different versions of the tool, small improvements. Clustal W, I think it was the first version. Then Clustal Omega, Clustal O, there are different versions of the same tool with small improvements, just like Blast. Like Blast has PsyBlast, Mega Blast. Developers of these tools continuously, Clustal W, they continuously improve. So there's in Japan, there's also a link to Clustal W output format. So let's see whether they have a version here. No. Yeah, but yeah, they're different. So Clustal, oh, there's even Clustal X. So it's actually the website, the actual homepage for Clustal W is, there's Clustal W2, Clustal X. There's the classic Clustal, no, Clustal X is the GUI version, the command line version. So this is the classic, original Clustal W is the first thing, and then Clustal Omega is the latest version of Clustal. Fast and scalable, can align hundreds of thousands of sequences an hour, greater accuracy due to new HMM alignment engine. So this one probably does not use hidden Markov models. Clustal Omega uses the hidden Markov models, and also Clustal Omega right now is just command line and web server, but just like Clustal X, GUI is going to be available soon. This is what they say, but so they're different tools. Usually, one should try these T-Coffee, Muscle, or Clustal. I mean, if you're analyzing sequences with certain similarity, they will probably be producing similar results to each other. Okay, so if you just use Clustal Omega, I think that's nobody. I mean, if you're in your research, if you need to do multiple sequence alignment, and if you use Clustal Omega as part of your experimental protocol, no reviewer is going to ask you, why did you use Clustal Omega? Why didn't you use T-Coffee? They're not going to do that. Okay, they're just, I mean, again, if you use T-Coffee or Muscle, again, nobody's going to question, why didn't you use this one? They can just be used in place of each other. They produce similar results most of the time. But to be on the safe side, I would recommend you maybe run at least 3 of these tools. Let's see whether maybe just use their common parts in the alignment, like an approach where a consensus approach where you get the results of these 3 alignments and put together the conserved parts that are shown in all 3 multiple sequence alignments will even make it better than using just one tool. All right, so yeah, after the midterm exam, we are going to continue with phylogenetic trees, where we are going to cover this guide tree building, algorithms, neighbor joining, and UPGMA. And in the midterm exam, so expect questions, as I said, some brief, short answer questions about some basic terminology, not too detailed. For example, I would not ask what's a xenologue, but you should know what a homologue is. In general, the terms that we use a lot: homologue, gene, protein, amino acid. these terms are Blossom 62. What's a scoring matrix? What is a substitution matrix? Or what is a position specific scoring matrix? What's a PSSM? What's a profile? These terms now should have some they should ring a bell now if you are able to follow the course. So if I ask questions about the first week's topics, they're going to be these short sentence, short description like questions that I may ask. And then the main thing is this dynamic programming. So there will be definitely one question about dynamic programming, the pairwise sequence alignment. Either fill part of the table or fill the whole table. And trace back the partial scores table to give the alignment. There will be a question like that. And the statistical significance of alignments, we have seen what does e-value means, some statistical significance measures, so you can in general know what they mean. You shouldn't memorize formulas, any formulas, since this is like going to be an open book exam, which you'll be able to refer to the slides during the exam. You shouldn't memorize anything. So suffix trees and suffix arrays, I may again give you one sequence and ask you to build its suffix tree step by step. At every iteration, show how the suffix tree looks like in every iteration. Or I may give you a suffix array and ask you to search for a pattern. So you should know what suffix trees and suffix arrays are. And in terms of profiles, we have seen how to represent a sequence with these percentage-based representation, and PSSM, position-specific scoring matrices, how we represent them, what the scores mean. And after that, we have seen hidden Markov models, given a multiple sequence alignment, how to build a hidden Markov model. So what we have done in you're doing in your second assignment is what is covered by hidden Markov models. And multiple alignments, we have seen three algorithms: the greedy algorithm, star algorithm, and the cluster W algorithm. Cluster W we have just seen and the overview of it. But if I give you, you should be able to, for example, if I do star alignment, if I give you pairwise alignments between a number of sequences and give you some match mismatch score, you should, by using that, you should be able to build a multiple sequence alignment of these sequences, K sequences, by using star alignment or greedy alignment that we have seen. Okay, of course, if I give you what the scoring mechanism is. And that's it basically. These are the topics that we have covered, and I will be happy to answer your questions if you have any. And you can always send me email if you have questions during the weekend. I will check my emails in the weekend too, so don't hesitate to send emails after hours or in the weekends. Yeah, the good thing about email communications is that even if I'm not available, it's okay. You can just it's just sending a letter, right? As soon as I'm available, I'll get back to you. Okay, so don't hesitate to send me email anytime you have questions. All right. Yeah, and substitution matrix and scoring matrix, they are the same. Exactly. A good point. They are scoring matrix, substitution matrix. They mean the same thing. But position-specific scoring matrices are different than substitution. They are like substitution matrices, which are computed for each position of a profile separately. So you can when you think about position-specific scoring matrices, that's like a profile. But in the profile, we have percentages. Here, instead of percentages, we have scores showing that what will be score of aligning a certain type of amino acid to that specific column. So it's like, that's why the name is really actually intuitive. Position-specific scoring matrix. So position refers to that column in that profile. So each column tells you what is the score of aligning type amino acid type A to this column, or what is the score of aligning type A to this column. So that's basically it. Yeah. If there are no questions from you, we can finish today's lecture. So we started late, but we are just finished 4 minutes late. That's good. I'll stop recording now.